All right, so now we're going to be talking about nuclear fission. As you can see, the name fission and the image here means one nucleus that is splitting, breaks down into two different nuclei. Okay, you have one nucleus at the beginning that breaks down to give two different nuclei. And this usually happens when the nucleus is a very heavy one. It's heavy and unstable. Okay. So you have a neutron hitting a uranium-35 nucleus and it causes it to stretch and fly apart, as you can see right here. You have a neutron that hits this nucleus and it causes it to be unstable and therefore divide. Okay. So energy released when this happens, energy is released in the form of kinetic energy of fission, fragments that fly apart from one another, with some energy given to ejected neutrons and the remainder given as gamma radiation. So on this image, you can see you have one neutron that causes this whole nucleus to be unstable, thereby breaking into two different parts. So you have a chain reaction. So this can actually happen with so many nucleus. So imagine that you have millions of nucleus that are caused to be unstable by injecting several neutrons. These reactions are going to happen at the same time simultaneously, causing what we call a chain reaction. This is exactly what happens in the atomic bomb. So a chain reaction is initiated when the bomb explodes or when the bomb is caused to explode. So what we call the critical mass, the minimum mass of fissionable material in a reactor or nuclear bomb that will sustain a chain reaction. It's called the critical mass. A mass large enough to sustain fission at or above critical mass in large quantity of atoms, an enormous explosion can occur. So uranium-235 and uranium-238 and uranium-239 are different. No, they are not. They are just isotopes. Okay? They are just isotopes. They are all atoms of the same element. That's why you see we all call them uranium because they all have 92 protons. So we are going to look at one of the greatest work of Albert Einstein. So if you look at this relationship, E is equal to mc squared. So Albert Einstein in the early 1900s, what he discovered was that mass is kind of related to energy in one way or the other. So he formulated a famous equation E is equal to mc squared, which is the key to understanding why and how mass is released in nuclear reactions. So the relationship of the equation terms, the more energy associated with a particle, the greater is the mass of the particle. The mass of a nucleon outside the nucleus is greater than the mass of the same nucleon bound in the nucleus. The greater mass of the nucleon is evident by the energy required to pull the nucleon apart. Okay? So if when the nucleon lose mass in a nuclear reaction, the loss of the mass multiplied by the square of the speed of light is equal to the energy released. The mass difference is related to the binding energy of the nucleus. How much is required to disassemble the nucleus? So you have this graph that illustrates that relationship. Okay? We're not going to focus so much on that. So let's check this out. Which of these nuclei has the greatest mass? Which of these nucleus has the greatest mass? Again, you need to check and see your periodic table and you realize that that mass is uranium. So realize that this is uranium. Okay. Now, the next one, which of these nuclei has the greatest mass? Again, we said it's uranium. Dividing the mass of a nucleus by the number of nucleons. Again, nucleons is protons and neutrons. In the nucleus gives the mass per nucleon. In which of these nuclei does the proton have the greatest mass? Okay. Although hydrogen is the lightest element, its lone proton has a greater mass than the protons in all the atomic nuclei. Hydrogen has more mass per nucleon. In which of these nuclei does a proton have the least mass? Ion. Ion has the least mass per nucleon, but the strongest binding energy. Okay, that's a graph that shows the mass per nucleon versus as it varies with increase in the number of protons. Again, another graph which we are not going to pay so much attention to. All right, just need to know that that is a graph for mass per nucleon versus atomic number. The graph of nuclear mass per nucleon versus atomic number of uranium, that's this one right here. The nucleon in a uranium nucleus have more mass than the nucleons in uranium fragment. Now let's look at nuclear fusion. Okay, fusion is the opposite of fission because in fission it breaks down, but in fusion it comes together. Okay, it comes together. So fusion is a combination of nuclei of light atoms to form heavier nuclei with a release of much energy. Any nuclear transformation that moves nuclear towards ion releases energy. Ion is the nuclear sink for energy production. A graph of mass per nucleon versus atomic number from hydrogen to ion. Okay. All right. So there's what we call thermonuclear fusion. It's a nuclear fusion produced by high temperature, resulting in more tightly bound nuclei. The mass decreases as energy is released. This is analogous to chemical combusting requiring a high temperature, where the end result is energy release and a tightly bound molecule. A solution is still being sought for reaction to occur under controlled conditions to provide an enormous amount of sustained energy. When energy is released by the process of fission or fusion, the total mass of the material after the event is less always because it is that energy that is converted, it is that mass that is converted to energy. All right. All right, so that brings us to the end of this unit.